for today, we play with a graph. And generally, a graph is, in most cases, associated with paths. So you have a path starting from one point to another point. And the classic problem that a graph may solve is a courier or a transport problem. So generally, if those nodes represent some geographic points or locations, you can represent the track or the path of a van or a courier by following those points. And in the end, you will have a graph. Okay, so we will take a similar problem for today in order to see how we can generate the graph. And here we have two solutions to generate the graph. One is to use a matrix, and the other one is to use a list of lists. Now, in terms of memory for huge graphs, the problem here, it's obviously can be easily solved by using a list of lists, because a matrix is inefficient. You'll have a lot of blank spots in that graph, so it will occupy memory. Now, another interesting thing for a graph is, for example, crawling the internet. And you can use the graph to design or represent the relation between links or between pages. Okay, so a graph could be simulating an internet. And if I'm thinking, I can have the perfect assignment for you to give you such a thing, and to, I don't know, try to compute a page ranking like Google was doing. Okay, so in order to determine which pages are important based on how many links are pointing to them and so on. So you see, for internet, that's another graph which we can use. Or a graph can also be if you represent knowledge. For example, you do a semantic analysis on content, and you know that in different languages, different combinations of words, they have different meaning. So that's another graph. Okay, so in that way, a machine can understand the meaning of a text. Okay, not just the text, but the meaning. What's the sense of it? What's about it? For example, if you have a text that contains Java, you could say it's about programming languages, but Java, it's also a coffee brand or a coffee type. So how a machine can know that page if it's about programming or about coffee? Okay, so graphs are very useful, but generally they involve huge amount of data. So that's why using a matrix is not efficient. Okay, so we will go for a list of lists. And in this way, you will see we'll actually, once again, recap the list part. Okay, so standard input output. And even if we go for lists, there is another decision that we need to make regarding how we represent the links between different nodes. So we can go for pointers, which are more efficient in terms of memory access, and or we can go for values. And yeah, we avoid pointers, but sometimes the operation will be less efficient. Okay, so standard input malloc. Okay, and let's say string.
Can we use a simple struct like last time, or?
Yeah. It's stuck into my head, so the last requirement. So I will go for a very simple structure. So let's suppose in order to cover a graph that could be a weighted graph, so there are different types of graphs. A weighted graph is a graph that has for each link a weight, a value. Okay, that could be a cost. Now you have directed graphs, which means the links have a direction. So they could be bidirectional or one direction. Okay, so these are other types of graphs. So in this case, we will go for a directional weighted graph, because we have these structures, locations. Okay, location with capital L, and okay, and yeah, but location is just a name. So let's say I will name this not location, but paths, or path. yeah, path, okay, between, or route. Yeah, it's better route. So a route has a destination, and that's it. Destination, and I will go for a fixed size destination. So that could be a city or an address, whatever. And this will be a float, the time, okay, needed to get to that destination from a point. Okay, so this will be our route. So we will draw an application which is able to manage this this for us. Okay, let's open the whiteboard. In this case, like I said, we have a weighted directional graph, which means we will simulate these different routes. So for example, we can start from, yeah, I need to reduce the size of it. Okay, so this will be Bucharest, okay. And from Bucharest, I can go to Ploiești, okay. It's a directed graph, so let's say we need 40 minutes, okay. From Ploiești, I can go to Comarnic, okay. And from Comarnic, I can go to Brașov, okay. So that will be our route. Okay, each has different values here, 30 minutes, I don't know, 60 minutes here. Okay, now from Ploiești we can go also to Ploiești, but from Ploiești we can go to, let's say, Cheia or Valeni de Munte, okay. And for here we can also go to Brașov, okay, we have this path. And for example, from Brașov we can go back to Bucharest by Buzău and back to Bucharest. Okay, so the paths are like this. Okay, so this is a directed weighted graph, which means we have values attached to each link, each arc. Now, if I should store this in a matrix, and that's why it's inefficient, because you see, in a matrix, you need to have the number of lines and columns equals with the number of nodes. So we have here 1, 2, 3, 4, 5, 6. So in that case, we will have a matrix with 6 lines, 6 columns. 1, 2, 3, 4, 5, 6. And the same columns, 2, 3, 4, 5, and another one here. Okay. So, and in this way, each line, each column is actually a source and a destination. So this is Bucharest, and this is also Bucharest. This is Ploiești, Ploiești. Okay, after that, let's say Comarnic, Valeni de Munte, Brașov, and Buzău. Okay, BB. And now if you want to draw this as a matrix, you know that if the cell at the intersection of a line of a column is different than 0, it means you have a direction, you have a link, and there you can store the weight. So from Bucharest to Ploiești is 40 minutes. From Bucharest to, from Ploiești to Comarnic is 30 minutes. Okay, and here you have from Ploiești to Valeni here, I don't know, maybe 60 minutes. Okay, so 60 minutes. Now, the matrix is a symmetric one. So it means that you have the same value from Ploiești to Comarnic and from Comarnic to Ploiești, which means I can write here 30. So in this case, the matrix will be valid, will be symmetric, sorry. So if I write here 30, this means that either the graph is bidirectional, which means any link is in both ways, or is explicitly both ways, which means I draw this. But generally, if the matrix is a symmetric one, it means you can go in both directions at any time. If it's not a symmetric matrix, it means you already know based on the value there in the cell that you have only one direction or both, which is the case now. Okay, so you see here you have a lot of empty spots, and just imagine what will happen if you have 1 million nodes, possible nodes. Maybe that's the graph of internet or a very small part of it. You will have a matrix with 1 million lines and columns, and sometimes that's impossible to store in memory, because a matrix is a continuous space of memory. Okay, so you need to have in heap this amount of memory without fractions. Okay, it's like you have it all or you don't have it at all. Okay, because a matrix, it's a continuous space. Now, the advantage of using a dynamic graph like this one is that you can have small available spaces in heap. So there you can store different nodes. Okay, so that's why it's much more easier to accommodate a graph like this one in memory. Okay, but here, how do we store this one? Okay, so this is the alternative with the matrix. You may say it's simple. Yes, it's simple, it's just a matrix. It can be very useful for small graphs, but for large graphs, that's not a solution. So how do we store the image of this dynamic graph? Okay, and here, this is this approach, a list of lists, which means that we generally create a main list which contains all the main nodes in the graph. So, and this could be a double linked list because it has the advantage we can move back and forward, or it could be a simple linked list. We will go for a simple linked list. Okay, so this will be Bucharest, and after that you have Ploiești. Okay, and after that we have it doesn't matter the order. Okay, you have Komarnik. Okay, and after that we have Brașov. Okay, is this one here? Let's say BV, Brașov. Okay, and after that we can have Valen, this one here, and the last one is let's say Buzău. Okay, the last B here. Okay, so initially we will have this yeah, let's zoom out, main list of nodes. So the main role of this list is to store all the nodes, all distinct nodes in the graph. So now how do we store the relations? That's why it's called a list of lists. Okay, so it's like very similar to chaining, but there we had an array of lists, okay, for hash tables. So now each list here will manage the head of another secondary list, which is actually the nodes directly connected to the current node. So from Bucharest, we can get only to Ploiești. Okay, and that's it. And here you also store the weight, the value, which means 40. Okay, so here we have 40. Okay, now from Ploiești, we can go to Komarnik. And the weight here it's 30. Okay, and also from Ploiești, so all the nodes which are in this secondary list means they are reachable from Ploiești, from the parent node. We can go also to Valen. Okay, so 60. Okay.
That we can get from Komarnik to Valen, which is not true.
Sorry?
Doesn't that connect also the Komarnik?
No, this is the difference. Because you see, all the nodes in the secondary list are actually the nodes from which you can directly grow from this node here.
Okay.
So this is like, this is the source and these are the possible destinations. And having Komarnik and Valen here, it doesn't imply any relation between the two. These are possible destinations, direct destinations from this one. So this is the source always. Now, from Komarnik, we can go only to Brașov. Okay, and that's it. Okay, from Brașov, we can go to, yeah, and from Komarnik, you see, we can go back to Ploiești. So once again, I will add Ploiești here. But this is just to say that, hey, from Komarnik, you can go to Ploiești. Okay, and you get the idea, from Brașov to Buzău. Okay, and so on. Okay, now, this is a list of lists, but there is one question and we need to choose. Why? Because at some point we need to find routes. We need to traverse the graph. So I will ask you, hey, can you reach from Bucharest to Brașov? So you will say, from Bucharest, I can go to Ploiești. Okay, where can I go from Ploiești? Get to Ploiești, see Komarnik and Valen. And in this way, you can find the shortest path from Bucharest to Brașov, or we can find all the possible paths from that source to the destination. So here, maybe the operational research course can help you see other things, other problems that you can solve with the graph, okay? The postman problem, the courier problem, and so on, to find the shortest path and so on. Okay, so here, when we will traverse the graph, we have the ability to facilitate that or not. Why? Because you see here, when you are here in Bucharest, you know you can reach Ploiești. Now, how do you know which are the next possible destinations from Ploiești? And now you have two choices. Either we store here the value. So here we just store Ploiești, and that's it. So you just store Ploiești. And now in order to find the possible destinations from Ploiești, we need to go back here in the main list and find the node with the name Ploiești. And in that way, we find its destination. So this is one solution. Now, the other solution, the faster one, is to store here not the name of the node Ploiești, but its address. So instead of storing here, so this is version 1, either we store here Ploiești, okay, the name, yeah, that's Ploiești, whatever, it's written with the mouse, or the second version is the address of Ploiești, of this node here, which means it's like here we can have a pointer which points to this one. Now, why the second version is faster? Because you don't need to go through this main list to find the node of this destination. Because if you have its pointer here, you have direct access here. Okay, so one solution involves a pointer, okay, a syntax with an asterisk. So we need to pay attention when we create this stuff. And the other solution involves a value. Obviously, the value, it's much more easier from the syntax perspective. But after that, how we find the destination here in order to find the locations from which we can get from that, to get from that, means a recursive search if we go by value. But if you have the pointer here, we already have the address of that node. We easily find what are other destinations from there. Okay, so this is the decision we need to make. Now, despite that, it's still a list of lists. Okay, so it's clear the difference between storing the value versus the address.
Yes.
Okay, so let's go back to here. So the route is actually the destination and the time, okay, for that. Now, so we know we need a main list, which is a simple linked list. Okay, so in this case, I will have the main list. I don't think this route will be helpful because, so this is the main list, let's say main list node. Okay, so what do we store here? We store the destination name, and I think the route, yeah, it's out of context because here I need to separate the time from the destination. You see here we are storing just the destinations. So this is the main list node. Because this is a simple linked list, we have the next pointer. Okay, it's obvious. And now here we need the address of the secondary list. So let's define it here. So these are destination nodes. Okay, so it's still a simple linked list. So this is the destination nodes next. So this is the secondary list that stores the destinations from a main list node. Okay, and this is the primary list that stores the distinct nodes from the graph itself. Okay, so this is the crossroad. Okay, so how do we store? We store it by value, okay, or we store it by address. So I will give you a very fast poll. So how do we, I'm just creating the poll, how do we store the destination? Okay, and you have two options: by value, which in our case means by the destination name, or by pointer, by address. Okay, by address, which means main node address. Okay, so I will give you the poll now. Okay, just a minute. Okay, so please vote. And let's see what the majority decides. Okay, so we have 17 out of, okay, 18 out of 24. Let's wait 5 more seconds. Okay, so let's end the poll. So you see the results: 12 by address, 6 by value. Okay, so let's go by address. Okay. Okay, so we are back in Visual Studio. So here, what do I need to store? The address of the destination, which means we will have in the main list the nodes like Ploiești, Văleni, whatever, Buzău. And now here I need to store the address of this node here. So let's say main list node, destination. And because this is the, here we store the destination, and also we need the information regarding the weight, the cost. Here we will have the time. Okay, so this is the route time. Okay, so in this case, the route structure is not needed anymore. Now, if we, let's compile this. Sorry?
The structure.
Yeah, we can delete it. Okay, so let's delete it because, yeah, okay. So let's build the project again, build, rebuild. And remember, you have a compiler which is doing only one traversal from top to bottom. And now here, you see you have this very strange error, which is actually saying nothing. And now if you don't know how to handle it, you can ruin the entire solution. So it's saying missing semicolon before asterisk. Now, the problem here is, remember, you have a compiler which is doing a traversal from top to bottom, a single one. It's a one run compiler. Okay, so in that case, the problem here is that when he compiles, he checks this line, this type doesn't exist. So this is like calling a function from another function. So in order to announce the compiler that it needs to wait, this is a type we define, you need to define it here also, struct main list node. Okay, build, rebuild. And now everything should be okay. Okay. So when you have structures and one structure is using the other one type, and you have this cross references between them, in that case, you need to instruct the compiler that one of the structures is defined later. Okay, so this is the destination node. You see, we have the next of that, we have the main list node pointer for the destination, and I have the time, which means that's the cost of going through that link. Now, if we go back to the main list node, so each main list node has the destination, it has the pointer next, but it also has the head of the destinations. Remember, we have this image here. This one here, you see each node here has the next pointer, but also has a pointer to the secondary list head. Okay, So, which means we have a destination nodes, destinations. Okay, so a lot of pointers. Okay, it's like walking on a minefield. So yeah, let's start with the easy part, and in that time maybe we clarify our mind. So the first thing that I want to do is to initialize the destination node or to initialize a main list node. So we need this kind of stuff to separate from everything else, and there are main things to do. So let's do, we know how to write these functions. We can't avoid them. Even if we remove the details, we need these functions. So destination nodes init destination. Okay. What do we need here? We need the pointer, the address of the main list node. And this is input value. Sorry. So this is main list node. So this is the node address. Okay. And also we need the time, float time. Okay, so let's create one destination node. Sorry, let's use the singular. So here you have destination node, not nodes, and also here and here. Okay. At some point I did this mistake and it followed me to the entire seminar. Okay, so destination node. Okay, just go for singular. Okay, so destination node, new node equals destination node, sorry, destination node asterisk malloc, and here I have a size of destination node, destination size of destination node. Okay, one of them. Now don't forget the next, and in the last seminars we forgot this, and you have seen what has happened when we tested. So next null. Okay, new node time equals time, and new node destination equals node address. Okay, because here we initialize the pointer to the value that we receive here. So in order to create a destination, it's obviously we need to have the main list. And like I said, this is the first thing that we will create, the main list of distinct nodes in our graph. Now let's do the same for the main list node. Init main node. So here we need the destination, and that's it.
You didn't return the new nodes.
Yeah, that's another classic. I think I know for sure that always the compiler will give me a compiler, so that's why I don't bother with this one. Okay. Okay, so init main node. Here we need only the destination, because these pointers here will be added because we will add destinations to that main node. Okay, so we just create an empty main node and that's it. So main node, new node equals main node, main list node, malloc, size of, once again, main list node. Okay, new node, next null. Now at the beginning we don't have any destinations, so null, and string copy new node dot destination. Okay, and return it, new node. So in this way we initialize the main node. Okay, now what do we need to do? So in order to create the main list, so in order to create destinations, we need to have the main list. Without that, you can't add destinations. Like in order to add Ploiești, as a destination to Bucharest, we need to add Ploiești in the main list. So we need a function that will add values in this main list. Okay, so once again, we have the insert method. And because we will have another insert here, we will cover, once again, as a recap, both ways. So here I will insert at the end, because this will be like a queue. Okay, you may say Bucharest will be the first Ploiești and so on. And when we insert in the destinations, I will use something like a stack. Okay, so insert on top at the beginning. Okay. So because here sometimes we may change the head of the main list. I will go as the example for trees. I will return this time. Remember when we did this, we were passing the head as a reference. Okay, so now I will just return it, and I will simplify the input arguments. So main list node, insert main node. And what do we receive? We receive the existing head. Okay, list head. And obviously we get the destination. Okay. Now let's create a new node. So main list node, this is the new node, and we init it. Init main node of destination. Okay, we have it. Now let's cover the cases. So this is insert at the end, right? Now, the special case, maybe the list is empty. So if list head is null, okay, this is it. We just return the new head, return new node, and that's it. So every time we call insert main node will be like head equals insert main node of head and so on. Okay. And in this way, I don't need to pass this by address. Okay. Now, if that's not the case, we need to reach the end of the list and attach the new node. So main list node P, starting at list head. Okay. While P next different than null, we just do this, P equals P next. So this will just traverse the list until the last node. And when we reach that spot, P next equals new node. Okay, so now we can do that. And this time, because we have a contract here, we just need to return the list head again. Okay, we have this contract. Now, maybe this is the thing that I don't particularly like for this function, because with the exception of when the list is empty, you need to pass it. You need to return it each time. So this makes sense only here. But okay, that's it. This is another way of writing insert. Okay, so this is insert into main node. So now we can insert into the main node. And if we can do that, it means we can create the insert into the secondary list. Now let's test this this function. So I will write here a function to print the main list. Okay, so print main list, and here I have the main list node, list head. Okay, so printf \n, the main nodes from the graph are. So once again, now if the, no, we can do this, main list node pointer P equals list head, and this I think will cover also the case where the list is empty, is null. While P is different than null, okay, this is a precondition loop, so it will check if P is different than null. So if you are in while, it means P is not null. So we can print it. Print F %s and comma, and here I will have P destination or city or whatever. Okay, maybe the name was not properly choose. Maybe this was should be a city or whatever. Okay, and P equals P next. Okay, so this will print the main nodes from the graph. So let's test this one. Okay, so we need to define a list of an array of strings in order to be to create the graph fast and to avoid typing. Okay, because that will be a very time-consuming operation. So let's define a char array. Let's see if I can do that like this. So these are cities. Let's say Bucharest, Ploiești, Bucharest. I think here it needs, yeah, it needs a const char. Yeah, that's okay. So Bucharest, Ploiești, Comarnic, okay. Brașov, let's say Valeni de Munte, and Buzău. Okay, so we have this array of strings, so I can easily use it to insert in the main list node. Okay, now let's define the pointer for that. So main list node, or we can define a structure that will wrap the main list node pointer. Do you want to do that, or to define, I don't know, map, a graph called map?
I think that's it. It's not a good idea because it will consume time.
Okay,
Yeah.
so we go for the pointer. Okay.
Yeah.
Okay. I will specifically ask Mihai if for the exam to ask you to do a wrapper structure for that. Okay. So, and to give you another half an hour extra time. Okay. So main list node, let's call this one is the graph.
Okay, then let's do a wrapper class.
No. The decision has been made. We need to live with that. Okay, that's it. We are adults, so we make a decision and stick to that. Okay, so so we have a graph here, which initially is null. This is our graph. So I will call the main list header graph. Now let's insert into this. So for integer I at 0, I less than, now here we can do easily mistakes, 1, 2, 3, 4, 5, 6. Okay, I plus plus. So the insert will look like this: graph equals insert main node graph, and the destination will be cities at index I. Okay, now if everything is okay, if we call print main list, we should see the cities. So this is, at this point, it's just a simple linked list with some cities. Okay, let's test this one. Build, rebuild. Yeah, my normal issue with let's take the value from here, with the string copy. Okay, so let me add this one here. Okay, let's give another try. Build, rebuild. Okay, no problems for me. If you have any issue, just let me know. Okay, so let's run it. Control F5. Okay, let me share with you on the console. So you see the main nodes from the graph are Bucharest, Ploiești, Comaric, Brașov, Valeni, Buzău. Okay, and the trailing comma, but yeah, we don't waste time to cover that case. Okay, so we know that at this point that we can create easily the simple linked list, the main list of the cities. In order to insert here in the secondary list, you see, in the destination, we need the main list node. And generally here you will get the destinations by name. It's like Ploiești, Văleni de Munte. So we need a function, because you will never know where Ploiești, Brașov is in this main list. You don't know their addresses. You know that they are there, but you don't know their addresses. So you need to get them. So we need here a function which we will use here when we will insert a destination in each main list node. Okay, so we need a function to return this for us based on the destination name. Okay, so this function returns the main list node for a given destination. Okay, so we need this function because it will be very helpful in order to get those pointers. So this function returns a main list node asterisk. So this is actually a function that search in a simple linked list. Okay, okay, and here I will have, let's call it search destination. Okay, const char destination, and that's it. This is the only thing that we need. And also we need the graph, okay, the main list. So main list node list head, okay, and the destination. Okay, so we need to return this value. Now if the list head is empty, let's cover the special case. So this, if this one is null, okay, we return null. And this is the way we can check the result of the search. If it's null, it means it's not there or the list was empty. Now, if the list is not empty, once again, I will go through the list, p equals list head. And while we didn't reach the end of it, p different than null, we do this check. If string compare between p destination and the given destination is, remember, string compare returns 0 if they are equal, -1 if it's smaller, +1. So I'm particularly interested in 0. So if this is the case, return p. And this is it. We exit while we terminate the function, we get the node. Now, if we exit while, it means it's not there. We covered the entire list. We didn't find it, so return null again. Okay?
Don't we also have p like p equals p next?
Sorry?
P equals, doesn't equal p.
Yeah, yeah. That's very valuable. Yes, because we will loop forever on the first node. Exactly. Thank you. Okay, so we need to move to the next one. Okay, and now I think it's okay. Okay, so in this way we can search through the main list by a destination, and you see when we find it, we get it. Okay, we get that node. So now we can insert in the secondary list. We can insert in this list because here you see, in order to init a destination node, we need the main list node address and the time. Okay, so let's write the function that inserts in the secondary list. So this was the function that insert a node in the main list. So now let's write the function that insert in the secondary destinations list. Okay. Here I said to you we will do insert at the beginning. So here we always return the head because it will always change. Okay, this is insert at the beginning. So here we are inserting in the secondary list, which is a destination node. Okay, insert destination. Now, what do we need in order to insert a destination? You need the main node, because if you have the main node, or we can ask for the, yeah, let's ask for the head of the destination nodes to keep it equivalent to the previous one. And here we will get from the main node the destination head, the destination list head, and we will pass it here. So this will be the head. Okay, and What else do we need? We need the destination node head. Yeah, we need the main list node. This is destination pointer. And we need the float, we need time.
What is this destination pointer?
Is this one here. Let me switch to the image. You see, we want to insert in the red lists, right?
Yeah.
Now, when you insert something here in the red list, you need what? You need the head of the red list, the secondary list. So we need its head. And here we said we will insert always at the beginning. But you see, inside each node here, in each red node, you have what? You have the address of the destination from here. So that's why we need the main node address. And this is the destination address. It's the pointer here. Let's imagine here, we insert in the destinations from Bucharest, we insert Ploiești. So what's the information that you need to insert Ploiești here? You need the time, 40 minutes. You need the address of Ploiești from here. Remember, we voted. We store here the address of Ploiești. We don't store Ploiești as a value. We store its address from here. Okay. And obviously you need the red list head. Okay. That's why you receive 2 pointers. One pointer is the head of the list, of this red list. The other pointer is actually the value that we store here. Okay. Because we established that here for destinations, we don't store Ploiești, Comarnic, the names. We store their addresses from the main list.
Okay.
And that will facilitate us later when we will traverse the graph. So that's why, yeah.
But doesn't main list node contain the head of its list?
No, the main list node of the destination pointer contains the head of the list of destinations for this city.
Yeah, that's what I meant.
Yeah, but now we will, let's say, insert. We are in the node called Comarnic, right? And
yeah.
We want to insert the destinations that we can reach from Comarnic.
Yes.
Which is Brașov only, right?
Yeah.
So we are on the main node called Comarnic. Now, when you insert in the destinations from Comarnic, you need what? You need its destinations list head.
Yeah.
Which is this pointer here from Comarnic, which is this one. This one, right?
Yeah.
So this is the first argument here. This one here.
But if we're getting the main list node, doesn't the main list node?
Yeah, but this node here will be Brașov.
Oh, okay, okay. I understand.
You know, is the destination from Comarnic.
Yeah,
so
okay.
If you want to insert a destination from that you can reach directly from Comarnic, you need the head of the list of destinations from Comarnic. Okay, and we need the address of the destination from the main list, which is Brașov.
Yeah.
And this is the time, 60 minutes. Okay?
Yeah.
Now, if you want, but this is another option. Here you can replace this with this, if you like. It's like source pointer. So here we can change the method to receive here Comarnic, Brașov, and the time. But because you have the source pointer, you can easily get its destinations head list, right?
Yeah.
So how do you think? It's more clear in this way or in this way?
Yeah, the second way I think is more clear with the main list node.
Okay, so this will be the source main list node, the destination main list node, and the time, right?
Yeah.
Okay, so we keep it like this. Okay. And this is called source pointer. Okay, so, and here we return. Now if we do this, then this doesn't make sense anymore. You see, you have a main list node, the main list node, and here we return a destination node. It's like, what's this? So let's write void here. So in this case,
we change the source.
Exactly. So we add another asterisk here. Okay, so here you have a source pointer, which is the address of the pointer of the source pointer, and so on. So we have another level of in direction.
Shouldn't we leave it like?
Yeah, I can copy paste it and edit. It will take me 2 minutes. Okay, so let's write it like this, and after that I will copy paste it and add the other version. Okay, and I will just do it, and you will have it on Git. Okay, so now what do we need to do insert into destination? So we need what? The destination node. Let's say this is the destinations list, and this is what? Source pointer. But this, remember, if you write this, is not your source pointer, is actually the pointer of the pointer. So yeah, now you have this fun thing to do. Okay, so in this case, you see is destinations. Okay, and now we get it back, the destination list. And like I said, here we will always insert at the end, at the beginning. So we have the destination pointer and float time. Let's create the new node, new destination, init destination. So you have the destination pointer and the time. That's very direct. So we just created a new destination. So what I will do, add this new node at the beginning at this destination list. And because this is insert at the beginning, I don't need to check if the list is empty, because generally adding a new node at the beginning means this: new destination next equals destination list. So if that's null, next equals null is the same. Okay, and now source pointer destinations equals new destination. Okay, so this is inserting at the end and adding a new destination in the destinations list. Now the other version, so here we had a destination node, and this was the destinations head, and we returned this each time. This should be like this: new destination is always created no matter what. Okay, and now destinations head, new destinations equals destination head, and now you return new destination. Okay, so this would be the other version of it. Okay, so let's say this is second version. Now you can have both functions in the same time. This is overloading. Okay, the parameters list are different, so we can keep both. Okay, so this is would be the other way. Okay, so let's create a graph. We have all the ingredients, which means I can go through the main nodes and I will create links between them, okay, by using either of these two methods. Okay, so but I think here we need the source pointer in order to get it. Yeah, I think we can use it like this. No, I will not add another function to increase the complexity. So how do we use these functions? So here we just created the main list. Now let's add links between cities. Okay, so what I want to do is to add relation between Bucharest and Ploiești. Okay, so in order to do that, I need to call insert destination, main list node, source pointer, destination pointer, and time. So we have a function that is helping us to get the destination. Okay. Yeah, because I will copy paste. Let's write this function here. So void add route. So what do we need here? Const char asterisk source const char asterisk destination and time. Okay, and in this way main will be much more clear. Now in order to, I don't know, maybe you can return here an error code if you want. Now the first thing that we want to do is to see if the source and the destination are inside the graph. So here we need the graph, main list node graph. Okay, now remember, this is not changing the main list. We are just adding in the secondary lists. So this is not changed. You pass it as it is. So the first thing that I want to do is to get the main list node, the source node. So this is equal search destination in the graph and search for source. And we do the same stuff for destination node. Okay, and here I have destination. Now, if any of these two does not exist, we can't insert it. Okay, you can't do that. So let's validate. If source node equals null or destination node, sorry, destination node with small d, destination node equals null. So if either of the two are null, return. We can't insert it. So this is our validation. Okay. Now, if they exist, I will show you how to call with both insert destination. Okay. So for example, the first version will be this one, version 1. And after that, I will just comment one of them. So here you need to pass what? Insert destination, the address of the destination. So insert destination. So here you see it needs the second version, the address of the source pointer. So this means address of source node. Okay. And destination pointer is destination node and time. Okay. So this is how you should call or insert using the first version of the method. Now, using the second version of the method, here you don't see this, but you see this part. Source node, sorry, destinations equals with insert destination of, again, source node destinations, destination point, destination node, time. Okay, so this you have it. Either way is the same stuff. And here it's clear the difference. Now here you pass this value by its address, so you can change it inside the function. Here, because you pass it by value, the pointer itself, you need to get it back if this is going to change inside the function. So yeah, you have advantages and disadvantages. Okay, none is perfect, let's say. Okay, so I will stick to the first one, or we can run with one, test the other one. Okay, so now at this moment we can print the print main list. Let's print the graph, which means I will print the main list, and after that for each node I will print the destinations. So in this way we see the graph and the times, and we know we have created the graph correctly. So this is a method which prints the graph, print graph. So we need main node, main list node, this is the graph, and that's it. So the first thing that I will do, let's put something here on the screen, \n. Okay, so I will print the main list graph. And after we do that, I need to print each destination, all the destinations for each source. So, sorry, main node, main list node P, starting with graph destination, because we need to start from each sorry, graph, no, starting with graph. Okay, so while P is different than null, here is what we will do. So printf destinations from %s and backslash n at the beginning. Okay, and here I will have P destination. Okay, and now I will iterate through the secondary list, which means destination node Q starting with P destinations while Q is different than null. We do this, print F %s and the time here %d, okay, and the comma. So the first value is the name of the destination, which is Q arrow, it's a comma here, Q arrow. So it's destination, and this inside the destination, remember this is the main node pointer. This is another pointer. So now we have the destination. That's why I think it was better to name the main node char array city or whatever, because now it may create confusion. And the time is Q time. Okay, don't forget to move to the next one. And also don't forget to move to the next one in the main list. Okay, and this is the graph. So what do? We iterate through the main list nodes, and for each node there in the main list, we iterate through its destinations list, which is the secondary list. Okay, so this is a list of lists. So that's why for each main while iteration, we have a while which goes through the secondary lists. Okay, build, rebuild. And now let's see. Let's add links between cities. So we have this function here, add route. So let's add routes. Add route. What? Now here you don't need to make mistakes because you need to keep the values, they are case sensitive. Okay, so destination is Ploiești. Okay, the time 40 minutes and the graph is graph. Okay, Control D. For example, from Bucharest, let's say we can also go to Buzău. 90 minutes. Okay, let's add another one from Ploiești to Comarnic. 30 minutes. Okay, also from Ploiești, we said we can go here. 80 minutes. And just to close the loop, from Comarnic, we can go to Brașov. Okay, let's see. Build, rebuild. Control F5. And let's see what will happen. Now, I see only the main list because I forgot to call print graph. So let's print the graph. Print graph, graph. Okay, so let's give another try. Okay, let me show you my console. And this is it. Okay, so the main nodes from graph are Bucharest, Ploiești, Comarnic, Brașov, Volendam, Buzău. Destinations from Bucharest, Buzău, Ploiești, 0. Okay, that's not okay. I think I forgot to initialize something.
No, it's type float and you
yeah, it's
type
float.
int, you know.
Yeah. Classic, another classic. Okay, so here it's %f. Yeah, let's control F5. Okay, let's see the console. Yeah, now it's okay. We can do to stop at 2 decimals, but now I see the values 90, 40, 80, 30, 80. Okay, so this is the graph. Okay, so right now we have it. Let's test the other method. So let's be sure that version 2 is working. So I will just comment this one here, version 1, and run it again. We should get the same output. Okay, here it is. So both versions of insert, they run in the same way. Okay, and yeah, and now we have a working graph. Okay, you have weights, and you can easily determine from each node where you can get, because you have the destinations, and from each destination you can reach other destinations, and so on. For example, if you want to do a traversal to see, it's like you go on a trip and you don't establish the destination. Okay, just to give you a glimpse, because actually here you need to cover, you have the two ways of traversing a graph, is the deep first or the breadth first. Okay, either is like simulating multiple task going through the graph, or a single task. This is deep first. Okay, it's like you go and try to find all possible routes, and the breadth first is like you split at each cross into multiple actors, and each is following a different path. Okay, these are the main algorithms, and you have the algorithm that you can use in order to determine if there is a route between a source and a destination, and that's the Dijkstra or Dijkstra algorithm. And after that, you have the shortest path algorithms and so on. Okay, which are, let's say, more specific to operational research. Okay, now the last function will be like, let's see what we can get from Bucharest. Okay, so this function is called just go. Okay, we have the const char asterisk source. Okay, we receive the main list node, the graph itself. Okay, so what we will do here, we will follow the first destination available from the current node until we reach a dead end, which means you reach a destination from which you don't have where to go. Okay, so a dead end. Okay, so what it means, we need to find the source. So main list node source node, okay, equals search destination in source graph. Okay, so let's say if source node different than null. Okay, now we know we have something to show. What's the problem here?
I think you wrote them the other in a different order.
Ah, yeah. Thank you. I didn't watch the IntelliSense. Okay, thank you. So if the source node exists, we do what? Print the location. So printf, we are now in %s, and write the name of the source. So source node destination. Okay, so in order to continue the road, and like I said, we will always get the first destination available. So in order to do that, we do this, and this will be a recursive call. Just go where? Source node destinations. And now this is a destination node, but we know it has inside a destination, which is the main list node. Okay, and the graph is the same graph. Okay, and this is, yeah, once again, the part with destination. We need to refactor that and call this city, okay? So source node destinations is giving you the pointer to the secondary list of the current node. Destination is the head, okay, is the value inside that head, okay, the head of the secondary list. And this is a main list node. And inside the main list node, we now have a const char 50, which is the destination name. Okay, now I think it's easy to refactor. If you go at the beginning and right-click refactor on this destination, this could be city name. Let's see if I can do that. Here, so this one, right-click refactor, rename, or you just rename. So here, let's call it city. Enter. I hope it will be everything okay. Yes. Okay. So now I think the line will look more readable. You see, it's source node destinations, destination city. Okay. This is the main list node, and now this is the name of the city. So let's see, where can we go from Bucharest by just following the first node. Okay. So here, just go Bucharest and the graph. Okay, let's see. Control F5. Okay, and this has happened. So destinations from Buzău, we are now in Bucharest. We are now in Buzău, and now it has generated an infinite recursion because we just found a loop. Okay, remember, from Bucharest we can go to Buzău, and I think from Buzău we can go to Bucharest, if I'm not mistaken. Yeah, let's test the loops here. Or not. So from Bucharest we can go to Buzău, but from Buzău we can't go anywhere. So why here? Let's see, I got a strange error code. So if source node, yeah, let's put a breakpoint here. Let's see why we have the error here. So the source node now is, I'm waiting on my Visual Studio to start. Okay, let's give it another try. F5. Let's close the, yeah, F5 again. Okay, now we are good. So source node, you see it's Bucharest. Next is Ploiești. This is the next node in line. And here you can check how the memory of this object of this articles looks like. So city is Bucharest. Next is Ploiești. Okay, next of that is Comarnic. So this is the main list. And destinations you see is destinations from Bucharest is what? Is Buzău. Yeah, next is Null. Okay, destination is Buzău. Okay, I think here, no, we have a problem. Let's see. Bucharest, no, from Bucharest we can reach Ploiești and Buzău. And we didn't see that. Control F5. So yeah, that was one of the things that I was afraid. Control Z. I think refactor didn't work. So let's see. Okay, let's try. Okay, so now we are back. Sorry for that. You see, bad design again, how some decisions we made at the beginning. Okay, so if rename work for you, it's great. I will not try it again. Now, the idea is that we are not checking. What we are not checking? If the source node destinations. Okay, so let's see. If source node, okay, source node destination. Yes, because if this doesn't exist, you are right. If this doesn't exist, if source destinations does not exist, is null. So we can't ask for a null pointer to give us the destination and the destination. Okay, so if, yeah, and I will not do the rename again. I will leave it like here. So if that will fix everything, it's okay. So just add this one. So if source node destinations is different than null, okay, then we do this. Okay, other than that, we return. Now let's see. New share. Okay, but now I didn't, when I control Z, I have removed the call to just go Bucharest graph. Okay, so now I'm not calling the method. Okay, Control F5 again. Okay, new share a console. Where is the console? Just a moment. I lost it. So Control F5 again. New share. Okay, so you see destinations from Buzău, and now we are now in Bucharest. We are now in Buzău. Okay, so by following the first available destination from Bucharest, remember we inserted the head. So initially it was Ploiești, but after that we inserted Buzău. So if I change the order of the destinations here by just changing the order of these lines, now if we just go from Bucharest, it will be Ploiești, and from Ploiești we can reach, I think, Vălenii de Munte. And if we add another route from Vălenii de Munte to Brașov, in the end, we will reach Brașov. So if I run this again now, Control F5. Okay, new share. Now you see, we are now in Bucharest, we are now in Ploiești, we are now in Vălenii de Munte. Okay, so now it's just following the first possible destination from each location. Okay, so this is a graph implemented by a list of lists, and we stored also the cost or the weight, so you can actually solve other problems like the shortest route by time or the shortest route by number of nodes, for example. You have algorithms for that. You can traverse the graph, and remember you have the deep first and the breadth first possibilities. Okay, so this is an example, like I said, of a graph as a list of lists. For a matrix, you have a matrix, and there you just apply the algorithms that you may know from operational research. So you don't have this complexity there because it's just a matrix. But the problem there is that for large number of nodes, for large graphs, you can't store that in memory. It becomes quite difficult to store it. Okay, that's all.